Hi guys, this is topic 54. Topic 54 and 55 go together. We're going away from integrals now. We've learned everything that you need to know about integrals. So now we're going to talk about just this one topic, which is called logistic equations, or really logistic differential equations. So we've already done differential equations. Remember, differential equations is when you separate variables, integrate each side, use your initial condition to find C, and solve for Y. These are logistic differential equations, which are going to look a little bit different. So let's do a little bit of review and then we'll get into the new stuff. So in exponential growth or decay, we assume that the rate of change of increase or decrease of a population with time is directly proportional to the population, or dp dt is equal to kp. So this is a differential equation because it's got a derivative and it's got an equal sign. So exponential growth or decay, the graph's going to look like, oops, see if I can get that thing to stop moving. Let's erase that and try that again. All right, so exponential growth obviously looks like that. And then it would go along the x-axis to negative infinity. However, in many situations, population growth levels off and approaches a limiting exponential number L called the carrying capacity. If you're in my environmental science class, you're very aware of this graph. So because of limited resources, we have a specific carrying capacity. In this situation, the rate of increase or decrease is directly proportional to both P and L minus P, so the carrying capacity minus P. P is usually going to be like the population growth or the population that's affected. This type of growth is called logistic growth, or gives you a logistic differential equation. So it's modeled by the differential equation dp dt is equal to kp, and then you have L minus P as well. Okay. Now, if I were to distribute this, I'd have one term with P in it and one term with P squared in it. So that's another thing to look for, especially if it's not factored. And when it's in factored form, that's the form that you actually want it in. So if you're in my environmental science class, you've already seen this. So the carrying capacity would be this line here. The growth is going to start out exponential, but then it's going to level off right at that carrying capacity. Okay. And that's the kind of curve that you get from this logistic differential equation. With what's going on now in the world, the COVID virus would grow exponentially. Our hope is that after we get through this exponential growth, it's going to start to level off, and the people that are most likely to get affected by it are the ones that got affected by it, and everyone else is going to be fine. So we can find the second derivative by taking the derivative of the first derivative, and that can also give us important facts about the time when logistic growth is the fastest, and we'll do this with an example from below. All right, so this first example, the population P of T of fish in a lake satisfies the logistic differential equation. dp dt is equal to 3p minus p squared over 6,000, where t is measured in years and p at 0 is equal to 4,000. That, as you know, is my initial condition. And again, I'm looking for this one. This one's not factored, so I'm looking for a p term minus like a p squared term. It's actually better to look at it in factored form, but we'll do that later. So we're going to go through the motions of this one first. So what's the limit is t goes to infinity of p of t is equal to what? So actually we're going to go ahead and let's go ahead and factor it, because that is actually easier to look at. So dp dt is equal to, now I'm actually going to factor out p, because both terms have a p, but I also want to factor out this 1 over 6,000 too, or sometimes you'll factor out a 3. It depends on the actual equation. So let's factor out the 1 over 6,000. So we're going to factor out 1 over 6,000 and then p. Now if I factor that out, that's like dividing this out. So 3 divided by 1 over 6,000, that 1 over 6,000 will flip over and become times, and 6,000 times 3 gives you 18,000. And then minus, and then I factored a 1p out, so I just have 1p left, and I factor out the 1 over 6,000, so that just gives me p here. Okay. That's actually the form that you want it in. And on the AP test, sometimes they give it to you in that form, which makes it even easier. So as time goes on to infinity, there's two things to notice about this curve. And let's go ahead and put the curve down here. So logistic growth curves all look the same, something like that. And this should be flat. So, okay. And then my carrying capacity is right there. Sorry, it's a little hard to draw this, but this one should be flat as well. Okay. So you can see a couple, quite a few things about this graph. One is this graph is always increasing. This is the actual graph of the function. And remember, this is a differential equation, so this is the derivative. So to take a derivative off a graph is the slope of the tangent line. So the slope of the tangent line should be 0 when you start off, and then 0 when you end up. And once it's factored, that makes it easy to see your zeros, because if I set that equal to 0, this would be when p is equal to 0, or when p is equal to 18,000. So the limit as t goes to infinity, and this would be my t value, and this would be my population that's affected, p of t. As t goes to infinity, this is going to level off at the carrying capacity, which is 18,000. So the limit is 18,000. And then what is the range of this curve? Well, it's starting at 4,000. I kind of started at 0, but we'll pretend that's 4,000. So the range for this one would be from 4,000 to 18,000. And it's not going to touch 18,000, so the only one that really would have an equal sign would be that one. And these are less than symbols. So that would be your range. Okay. Looking back at the graph, another thing you can see is it's increasing at an increasing rate. So it's increasing in concave up until you get to about that point right there. That's a point of inflection on this graph, and then it goes to increasing in concave down, or increasing at a decreasing rate as well. So for what values of p is the solution curve increasing? Well, that would be all values. So that would be from 4,000 to 18,000, because this graph is always increasing. And you'll notice this says values of p, not values of t, so I'm looking at the y values in this case. Decreasing would be never. Okay. And your justification for your answer, increasing means the first derivative is greater than 0, so my factored first derivative would be this. And I want to find out where that's equal to 0, which is 0.18. And then when it's greater than 0, well, as long as p is at less than 18,000, this will be a positive number, and this would be a positive number. So that's going to be give you a positive first derivative, so that would be increasing. Decreasing would be when p is greater than 18,000, because 18,000 minus the number greater than 18,000 is give you a negative, times a positive would be negative. But again, this graph never goes over 18,000, which is why this is never decreasing. So my justification would be because dp dt is greater than 0 for all p less than or equal to 18,000, something like that. And then for what answers of p is the solution curve concave up? Well, an important thing to know that I just want you to memorize is that point of inflection always occurs at half the carrying capacity. So if the carrying capacity is 18,000, this point of inflection right there is going to occur at half of that, which would be 9,000. So the solution curve is concave up for p in between 4,000, which is my starting point or my initial condition, to 9,000. And then it'll be concave down from p in between 9,000 and 18,000. And that's because my second derivative was either going to be positive or it's going to end up being negative. So does the solution curve have a point of inflection? Yes. And that would occur at p is equal to 9,000. And your justification on the AP exam, you don't actually have to do the second derivative, because all you have to say is because that is half the carrying capacity. and then use the information to sketch it. Well, I've already done that. And again, looking at the graph, it's actually easier to answer all these questions than it is to look at the equation, but you can look at the equation as well. But the graph tells you everything you need to know. All right, one more example. Again, this one's going to be pretty similar to that. So again, it's actually, this one is the exact same equation. The only difference is the initial condition is different. So now my initial condition is starting at 10,000. So if this is my carrying capacity up here at 18,000, and I'm starting at 10,000, well, 10,000 is more than 9,000, so that graph would just start above the point of inflection, and it's just going to go like that. So the limit as t goes to infinity is still going to be 18,000 because that's my carrying capacity. The range this time is going to be between 10,000 and 18,000 because that's my initial condition, so I'm starting there. Again, the solution curve increasing would be always, and I'm not going to write everything else out. Decreasing would be never. And again, that's because the first derivative is going to be positive as long as p is less than 18,000. Concave up for this one's going to be never because I'm already starting past half my carrying capacity of 9,000, so that's going to be never. And concave down would be everything else, so from 10,000 to 18,000. Does the solution curve have a point of inflection? In this case, no, because my initial condition is greater than the half the carrying capacity. And then sketch the graph. Again, it's just going to look like that. So the only time your curve's going to look like this is if you're starting above the half the carrying capacity, but below the actual carrying capacity. And then it's also possible that you start above the carrying capacity. So for instance, people dump a bunch of fish in this lake, and this lake can't support that number of fish, and then the fish are going to die off. So now my initial condition is 20,000, which is above the carrying capacity again of this factored out is 18,000. So the limit's still going to be 18,000. What's the range is going to be 18,000 to 20,000. And let's go ahead and do the graph. So there's my 18,000 carrying capacity. If I start here at 20,000, this time it's just going to come along that and reach that perfect 18,000 there. So for this one, would the solution curve be increasing would be never. Decreasing would be always, or from 18,000 to 20,000. Concave up is going to be always. From 18,000 to 20,000. Concave down would be never. Point of inflection would be no. And again, that's because your IC is greater than half the carrying capacity. And then I already sketched the graph of that as well. So big thing to know is that most of your problems on the AP exam are going to look like this first example here. So if they give you a logistic differential equation, again, you're looking for a p and a p squared term. If it's not factored, what you want to do is factor this out, because once it's in factored form, that tells you everything you need to know. So just looking at this, my carrying capacity is at 18,000. I have a point of inflection at 9,000. One other thing I should probably mention is that's the point where you have the rate of greatest increase, because you're starting to increase at an increasing rate until you switch to increasing at a decreasing rate. And again, excuse me, the slope of the tangent line gives you your rate of change or your derivative, so that's where your slope's going to be the steepest. So if I drew a tangent line there, it's going to be less steep. If I draw a tangent line there, it's going to be less steep. This is going to be my rate of greatest increase is always at half the carrying capacity. So with this COVID virus thing, that's kind of the thing we want to get to, is once this rate of increase starts increasing at an increasing rate, Once we know we are increasing at a decreasing rate, then we know that we're hopefully out of the woods on this thing. So let me go ahead and pull up your assignments so I can go over a couple things really quick on that. All right, so this one just starts off given this differential equation. The biggest thing I want you to do is factor this out. I'll give you a little hint. You want to factor out 0.002p from both of these terms so that you can see everything that's going on. And then answer all those questions. And again, you can basically answer these questions based on just the factored equation itself. Okay. And then they give you another initial starting point as well. Another thing this is used for, besides like carrying capacity of something in an ecosystem or carrying capacity of a virus, rumor spreading is something as well. Here they factored out the P, but I would probably factor out a 1 over 2,000 as well, because that's a little bit easier to see. Although most of you can probably look at this and see when this one's equal to 0. Obviously, this P is equal to 0 when P is 0. So you wouldn't necessarily have to factor this one if you can see what value of P is going to go here. And then I have some examples of multiple choice questions from previous AP exams here, just a couple ones to answer. Okay. And again, these are assignments that you don't have anymore because I hadn't copied these and given them out yet. So I'll attach them to this email. If you have a printer at home, I recommend you print them out and then just take a picture of them and submit them through email or through text once you have these things done so I can check and see how you guys are doing. If you haven't done the ones from 46 and 47, you need to get those done too because a lot of you guys still have not done those. We're going to have to keep up, so make sure you're doing that. You should be working on this class every single day. I'm going to post something at least every other day, but probably every day as well because it doesn't look like we're going to be coming back to school anytime soon. So I'll do that as well.